The second thing I'd like to show you today is something I hope you already know. I know that in my educational career, somewhere in elementary school, I had a teacher kind of show me these things. They're really cool little tricks and very helpful little tricks for doing things like simplifying fractions, and then later on it was good for things like factoring polynomials and business like this. I want to talk to you about divisibility theorems and ways of just looking at a number without having to actually divide things out and being able to tell, okay, that number is divisible by 2, that number is divisible by 8, that number is divisible by 5, and so forth. That's a very useful skill, and you know, I don't want to get into any big involved examples, applications where you need to know that kind of stuff, but I think you're going to see that it falls into place in a lot of places. You know, if I were looking at this fraction a over b, and I'm wondering, okay, when will that simplify to a whole number? Okay, well, it's going to happen when the denominator divides cleanly into the numerator, and we simply just say it divides the numerator. So that's the kind of thing I'm going to look into, is how can I look at this a and tell automatically that b will be able to divide into that. It's useful to us because sometimes I want to use whole number answers, and that has to happen, and if I can look at that and tell that it doesn't happen, I've got a problem. These are real easy tricks, and when I say grade school tricks, they really are. That's when I was introduced to them. You're not going to see any kind of really tough mathematics here. I will take, with the easiest ones, I will show you a little bit about where they come from, but some of them I'm just going to show you the theorems. We have several last digit theorems. No matter how many digits a number has, a numeral for the number has, we can express it as just a list of these digits. And what we do is we take all but the last one and we say, okay, you got that times a multiple of 10, that makes sense. And then you've got the last one plus the last one, right? And that's really the way our number system works, is a base 10 numeral system. And so I can take those things as a multiple of 10 and then just add the last one, okay? Now, if I were concerned about this big multi-digit numeral right here being divisible by 10, well, I've got a piece of this that is divisible by 10 already because it's a multiple of 10, right? That has to be divisible by 10. I could cancel the 10s out, for goodness sakes. So it really comes down to, if I look at these two numbers, this one and this one, this will be divisible by 10 if and only if this is divisible by 10. And the only single digit that is divisible by 10 is 0. That's it. Anything else, if I divide by 10, I get a fraction. Okay? So that gives us a quick and easy way to spot divisibility by 10. Just look at the last digit. If it's a 0, it's divisible by 10. I bet you knew that one already. Okay? I'm going to get a little tougher, but I'm starting with the easy ones. The same idea applies to divisibility by 5. Okay? This is already divisible by 5, so this will be if and only if this is. And what single digits are divisible by 5? Well, 0 and 5. And that's it. Right? What I'm asking is, what numbers can I divide by 5 and still get a whole number? 0 and 5. That's it. Okay? So a number is divisible by 5 if and only if its last digit is a 0 or a 5. Bet you knew that one too. Divisibility by 2 comes from this same concept. Being a multiple of 10, it's already divisible by 2, so this is equivalent to being divisible, this number being divisible by 2. And so what single digits are divisible by 2? Well, the even ones, right? 0, 2, 4, 6, and 8. Okay? So for each of those three numbers, all we have to do is just, I don't care if there's 120 of these numbers in front of it. Look at the last one. And that last digit will tell us then what's divisible, if it's divisible by 10, 2, and 5. Okay? Now, I might try to pull this stunt with 4, but let me show you the problem here. As a multiple of 10, this is not necessarily divisible by 4. It could be, but it doesn't have to be. However, there is a power of 10 that is divisible by 4. That's 100. If I take all but the last two, I could say that times 100 and then take the last two and put those together. And then I have the same basic setup. This is, being a multiple of 100, is divisible by 4 automatically. So this will be divisible by 4 if the last two digits are divisible by 4. So you can have a ton of them. I don't care anything about that. I just look at the last two. Probably, I should know my multiplication rules by now. I can tell if that's divisible by 4 much quickly than dividing the whole number out, right? 8 is similar, but 100 is not necessarily divisible by 8, so I bump it up to 1,000. And I look at the last three digits right there. So a number is divisible by 8 if and only if its last three digits are divisible by 8. And I'm not going to take the time to change it, but if I wanted to go to 16, then I have to look at the last four digits and see if those last four are divisible by 16. And then it's starting to get a little messy, but that's the idea. I can just look at those last digits. I can avoid all the previous digits. Okay? We also have some sum theories. These are really cool, where I can actually look at the sum of all the digits and tell if a number is divisible by 9, for example, or 3. A number is divisible by 3 if and only if the sum of its digits is divisible by 3. So this big ugly thing, rather than have to divide that out to see if I get a whole number, I can really just add up the digits. 14, 16, 25, 32. 32 is not divisible by 3, right? I get in fact, when I check this, I get a remainder of 2. And then when I check this, I get a remainder of 2 as well. The cool thing is, if I bump up any one of those numbers, it doesn't have to be the last one, any one of those. Let me change this, watch this, change the 4 to a 5. And change this 4 to a 5. And that makes that a 33. And then all of a sudden, my number is divisible by 3. It's really slick how that works. And you can prove that, but it's a little bit messy. I didn't want to get into it. 9 works in exactly the same way. I can look at this number and tell you that this 7,352,000 blah, blah, blah is not going to be divisible by 9 because 33 is not divisible by 9. Okay? And then the last one, this really kind of opens things up for the rest of us, is I can look at products of numbers as long as they're relatively prime. And what I mean by that is they have no common prime factors. For example, 4 and 9, this is made up entirely of 2's, this is made up entirely of 3's, so they are relatively prime. 4 and 6 are not because they share a 2 factor. And as long as they are relatively prime, then a number will be divisible by the product if it's divisible by both. So for example, I can tell you this number is divisible by 6 because it's divisible by 2, 4, right? It's divisible by 3 because I add them all up and I get 27, which is divisible by 3. And 2 and 3 are relatively prime. So there you go. You've got a theorem there for 6. It's also, if you look at it, divisible by 4 and 9 because if you look at the last two, that's divisible by 4. 27 is divisible by 9, so it'd also be divisible by 36. Trust me, you would not want to have to divide that by 36 to figure that out. Okay, so these are some good little tricks that you can use, and I've summarized them for you on a few pages that I'll flash up now.